Integrated Circuit 15 Digital Circuit CPU Design. Now the CPU design, the most basic operation of CPU is to add or subtract numbers, and you can have 32-bit or 64-bit operand A and B are two numbers coming from the register, and this register value is either added or subtracted and go back to the register as the answer. So this is a very basic CPU function. Now when you add a number, if A is 0 and B is 0, sum is 0. One side is 1, and both are 1, then become 0 again because bit to carry out, right? That's called a carry. For example, you add 3 plus 7, then it becomes 0, and you have a carry out bit. Now when you don't include carry in out, it's called half adder. Full adder. Half adder is simply, you look at this, the exclusive OR of A and B bit is going to be the same. Okay. Now you have a C carry in, carry coming from previous digit, and a carry out. So relationship becomes a little bit more complex, but not much. The sum is going to be A, B, C. C is carry, and the C0 will be either AB or BC or AC. Okay, so the full adder is written this way. So we repeat this 64 times for each bit. A1, B1, and A0, B0, A1, B0, B1, C2, A2, B2, A3, B3, so on so. Okay, 64 bit of them. Okay, so you have a simple adder. Say if you have a 4-bit, 1, 2, 3, 4, there is a C in, then you get this, and the carry propagate. Okay, so this simple adder, the problem is the worst case time it takes to complete the addition is going to be depending on carry in to carry out, and it's very slow because you have to go through so many gates. Suppose if you have a 64, it has to ripple through 64 adders, and CPU will be very slow. So the very standard way to deal with this is to use a carry-lookahead. The carry-lookahead is you have all the number for 4-bit and this one, and you make a separate circuit to figure out C0. Okay, so this circuit is going to figure out C0. It doesn't have to go through many gates. Okay, now if you have 16-bit adder, then you have a carry-lookahead for each 4-bit, right? And you have a what we do is we use this result to make another carry-lookahead for 16 times 4, right? So you can have 16-bit, 16-bit, 16-bit. So each 16-bit can have carry-lookahead, 4 of them, and 4 of them, and 4 of them, and each one has next level carry-lookahead. Okay, so finally, what we do is we use all the result to get final carry look ahead for 64-bit. So in this logic, you don't have to go ripple through 64 adder to get this final. You get only first stage logic, second stage logic, and the third stage logic. Okay. Now, typical CPU has ALU. The arithmetic logic unit, and this CPU does addition, and the worst case delay is dictated by carry look ahead. And this is a well-known technique to speed up the CPU. So when you have large number of bits, for example, double precision is a 128-bit you have to add, then carry look ahead become very helpful. Now, this kind of CPU perform addition, subtraction, and logic operation. Logic operation is like invert, or AND, or, and if kind of logic operation. That's a CPU's. If you see the assembly code, most of the code is executed by ALU, except for multiplication. You can handle multiplication using the software library. Means you have to add many times. And these days, since we have a LSI chip, we integrate multiplier right next to it, and we do multiplication separately. Okay, so multiplication and division is a very difficult operation. There's no good algorithm to do it in a pipeline fashion. Pipeline fashion means flow through. You have operand A and B, and each clock is proceed and get out. Say after 5 o'clock, the divisions come out. There's no such a things. Division is very difficult operation mathematically, and its only way known is to do step by step, subtract, check, and subtract, check kind of things. Now the improvement is made to do 2-bit subtraction. Means each subtract you advance 2-bit, and if 64-bit, it still takes long time. Okay, so division is a very difficult operation. Usually there's no hardware for division. It's done by software library. Multiply, most of the time these days have a multiplier hardware. So you put the operand AB and you get the C. Of course, size of C doubled after multiplication. The operand A is 64, C will be 128-bit, right? So those multiplier and the ALU will be the basic component of execution unit in the CPU. Execution unit means you handle data coming, operand coming from the register. And beside the register, there is the instruction buffer or cache. And from memory, instruction go there, data go there, instruction go there, and data go there. Some instruction contain the data, like 64-bit. You have a data field, and that goes to here. And what happened is this instruction is decoded instruction decoder, and decoder is loaded into state machine. This state machine is basically the regulate the data flow of the execution unit. It's tell you where to put data and which operation to do, logic or addition or subtraction, and where to return the result into the register. That's the state machine control. And this state machine is loaded up by instruction decoder. Okay, so this side is a control side of the CPU, and this side is execution unit. Of the CPU. So that's the way a whole chip is created. And if you look at the layout of the CPU chip, usually register is big because each bit is a flip-flop, costs a lot of gates, and CPU and the multiplier is very big too, very hardware intensive. And there is a cache from memory, and miscellaneous signal goes. This instruction decoder and state machine is very tiny bit, very tiny portion of the CPU. And if there is an on-chip cache for this register, that's going to be the biggest portion. Okay, so that's the CPU chip, conventional CPU chip. I hope you enjoyed this video. If you like, subscribe.